Hello everyone, I'm Shofei Zhu. In this video, I will present my paper, Learning and Programming Challenges of Rust, a Mixed Method Study. This is a joint work with authors from Penn State, Wisconsin, and China Telecom Cloud Computing. Rust is a young programming language designed to provide both low-level efficiency and high-level memory safety and thread safety. Rust conducts strict compiler checks to achieve this purpose. Rust's popularity is increasing dramatically these years. According to Stack Overflow surveys, Rust has been the most loved programming language since 2016. Rust has already been adopted to build many safety-critical software systems, such as OSs, browsers, and blockchain systems. Rust's safety mechanism centers around two important concepts: ownership and lifetime. The basic rule only allows value to have one and only one owner. The value is dropped when its owner's lifetime ends. To improve the flexibility of coding in Rust, Rust extends its basic rule to have multiple extended rules. First, Rust allows a value's ownership to be moved to a different owner. However, it does not allow any access to the previous owner after the move. Second, Rust allows to temporarily borrow a variable's ownership using a reference. A reference can be immutable for read-only accesses or mutable for read and write accesses. Rust allows multiple immutable references to a variable to exist at the same time, but it only permits at most one mutable reference to a variable at any time. All these rules are checked statically during compilation. They essentially prohibit having mutability and aliasing at the same time. They together can prevent many severe memory bugs and concurrency bugs. Unfortunately, Rust is known to have a steep learning curve and is difficult to program in practice. This is probably because of two reasons. First, Rust's safety mechanism is unique, and the related grammar is very different from traditional programming languages. It is very difficult for programmers to migrate their previous programming experience. Second, the design philosophy of Rust is to reject all suspicious code, and Rust safety checks are strict, sometimes overly so, making Rust code hard to be compiled. Let's take a look at a real-world example where Rust safety rules confuse programmers. Variables out1 and out2 are similar to each other, since both of them contain two full objects. However, out1 is an array, but out2 is a tuple. Function test takes two full objects as inputs. It uses a mutable reference to borrow the first full object and an immutable reference to borrow the second one. Function test is called here using the two full objects in the array as inputs, but the Rust compiler reports an error on this line. The reason is that the elements of an array must be borrowed altogether in Rust, since the Rust compiler conservatively assumes an index can access any element in an array. Out1 has already been mutably borrowed as the first parameter. Thus, it cannot be borrowed again as the second parameter. The second function call uses the two full objects in the tuple as inputs. Surprisingly, this call is allowed by the Rust compiler, because different tuple fields are borrowed separately in Rust. This example demonstrates the complexity of applying Rust safety rules. Besides the safety rule that a mutable reference cannot coexist with another reference to the same object, programmers must also know how array and tuple elements are borrowed. Without a clear understanding of these, it is very easy for programmers to make similar mistakes and write programs rejected by the Rust compiler. To systematically understand the programming difficulties of Rust, we conduct an empirical study on Rust-related Stack Overflow questions. We focus on questions related to safety rule violations. To conduct the study, we first build a taxonomy for the root causes of the violations. We then applied two statistical models to pinpoint when the safety rule is more confusing. Finally, we inspect whether the Rust compiler provides all the necessary information for programmers to comprehend the violations. We got 6 findings from the empirical study. To validate the findings of the empirical study, we conduct an online survey on Qualtrics. Besides directly asking participants for their previous experience in coding Rust, we also show them small programs containing safety rule violations and design questions to observe how participants comprehend the violations. In total, we receive 101 valid responses from real-world Rust programmers. We conduct extensive data analysis of the response to check whether they are consistent with the findings in the empirical study. We observe that Rust safety rules are difficult to apply in concrete coding scenarios. Sometimes, error messages provided by the Rust compiler may not be helpful enough. In total, we gain 6 findings about the programming challenges caused by Rust safety rules. Those findings can be useful references for Rust learners and programmers. Moreover, the findings are confirmed by the online survey with statistical confidence. This is the outline of my talk. I have finished the introduction. Next, let me introduce our empirical study on Rust-related Stack Overflow questions. We built 2 datasets for the empirical study. The large dataset is for statistical analysis. It contains all Rust-related questions on Stack Overflow. We manually inspect why programmers ask these questions on Stack Overflow. The 2 most common reasons are not knowing how to use the library and being unable to understand Rust safety rules. We can see that Rust complex safety rules indeed pose unique challenges to Rust programmers. Moreover, we build a small dataset for manual inspection. We first randomly sample 100 questions that are related to Rust safety mechanism. Each sampled question contains a code snippet for describing the problem. We then leverage the snippets to implement standalone programs and reproduce all described problems offline. In the end, we check the violated safety rules. Since some questions are about more than one violation, in total, we identified 118 safety rule violations. They are targets of our manual study. Our empirical study focuses on 3 research questions. First, we want to identify which safety rules are more difficult. Second, we want to pinpoint when the safety rule is more challenging, since intuitively, the same rule may be more confusing when applied to particular code constructs. Compile error messages are the most important feedback to programmers when their code violates the safety rules. Thus, in the end, we want to inspect how helpful the Rust compiler is. To understand which safety rules are more difficult, we first construct root cause taxonomy for safety rule violations. Lifetime and ownership are the 2 most important concepts in Rust safety mechanism. We first divide violations into those due to complex lifetime computation and those caused by violating ownership rules. We further divide each category into several subcategories. Lifetime computation may be much more complicated than referring to a variable's lexical scope. Programmers may estimate a variable's lifetime to be longer or shorter than it actually is, thus violating a safety rule. Based on where lifetime computation is conducted, we divide violations in this category into those due to interprocedural lifetime computation, those due to intraprocedural lifetime computation, and those caused by syntax errors when declaring a struct. An object's lifetime may cross a function's boundary. Let me show you an example. A function can borrow its input parameter. Here, function f mutably borrows the input bar2 object. Usually, the borrow terminates after the function call. However, due to these lifetime annotations, the lifetime of the borrow conducted by f is bounded with the lifetime of the borrowed bar2 object. Therefore, the lifetime of the mutable borrow by the first f function call does not only cover the whole function f, but also spans to the end of the function main, since the lifetime of the borrowed bar2 ends here. Thus, the lifetime of the mutable borrow overlaps the mutable borrow by the second f function call on the same bar2 object, violating the same safety rule that a mutable reference cannot coexist with another reference to the same object. Ownership rules can be divided into move rules and borrowing rules. Thus, for cases that violate an ownership rule, we divide them into those violating a borrowing rule and those violating a move rule. Misuse of references can cause borrowing rule violations. For instance, the violation we discussed at the beginning is due to mistakenly borrowing an array of objects altogether, instead of borrowing one single array element. Although the safety rules are relatively easy to understand, these two examples and many others demonstrate that the rules may be difficult to apply in concrete usage scenarios. After having the taxonomy, we then manually studied the 118 violations in the small dataset and put them in each category. There are 77 violations due to complex lifetime computation and 41 cases caused by violating ownership rules. More lifetime-related questions are asked on Stack Overflow than ownership-related questions, indicating lifetime computation is more challenging in Rust programming. The next research question is, when a safety rule is more challenging? We take two steps to answer this question. We first use code constructs to represent Rust coding scenarios and manually label code constructs involved in the violations of the small dataset. We then compute the lift correlations between violation root causes and involved code constructs. A lift value larger than 1 represents a positive correlation, and the rule is more difficult to be applied to the code construct. How to compute the lift between root cause A and construct B is shown by this formula. PAB represents the probability of a violation that is due to root cause A and also involves B. PA means the probability of a violation that is due to A. PB denotes the probability of a violation involving B. Among all code constructs with at least 10 violations, root cause interprocedural lifetime computation is more correlated with static lifetime annotation, self-defined lifetime annotations, and generics. For this example we discussed earlier, it is caused by interprocedural lifetime computation, and it involves self-defined lifetime annotations. Similarly, we also identify code constructs that are more difficult to be applied for the other three categories. From the results shown in this table, we can see that the same rule has different difficulty levels when applied to different code constructs. We take two steps in evaluating how helpful the Rust compiler is for debugging safety rule violations. We first conduct a cognitive task analysis to identify key steps in comprehending compiler error messages. Our CTA contains a think aloud observation and a semi-structured interview. We also invite external experts to inspect the identified steps. We then follow the CTA results to inspect safety rule violations in the small dataset and check whether information required in each step is provided in the compiler error messages. Among the 118 violations in the small dataset, for 8 violations, their programs can be compiled and do not have compiler error messages, but the compilation conflicts with the programmer's understanding of Rust. For 59 violations, their compiler error messages contain all necessary information. For the remaining 51 violations, their compiler error messages miss required information in some comprehensive steps. For example, the compiler error messages of the safety rule violation we discussed at the very beginning do not mention how array elements are borrowed, causing the programmer to ask how the safety rule is breached on Stack Overflow. In our paper, we further categorize what information is missed. Please refer to our paper for more information. Overall, the Rust compiler may not provide all information necessary to comprehend the violations of Rust safety rules. Next, I will introduce the online survey of Rust programmers. we designed a qualitative survey to validate the findings and the identified challenges in the empirical study. Our survey contains 3 phases. First, we ask participants demographic information and RAS experience. Second, we show participants several RAS programs and ask them to highlight when safety rules are violated, rate how difficult to comprehend the violations and how helpful the RAS compiler error messages are, and describe how the rules are violated using text in open-ended questions. Third, we ask participants several post-session questions about their overall technical background. To recruit participants, we distributed our survey advertisements by posting threads on RAS-specific forums and newsletters, and sent emails to programmers who recently committed code to open-source RAS projects. In total, we received about 500 completed responses. 3 paper authors inspected the responses together and identified 101 as valid. The valid responses are our analysis targets. Invalid responses are those finished in a very short time or having open-ended question answers identical to other responses. Among the 6 findings of the empirical study, we successfully validated 5 of them. Due to the limited time, I will only discuss 2 validations. Please refer to our paper for more details. To confirm RAS safety rules are difficult to apply in some coding scenarios, we show participants small RAS programs. All programs contain a safety rule violation. All programs are either directly from the small dataset of the empirical study or modified based on a program in the small dataset. For instance, we show participants this example we discussed. We explicitly tell participants that each program contains a safety rule violation and ask them to highlight program tokens causing the violation. The expected highlighted tokens for this example are the 2 parameters of the first test function call, because they cause one mutable reference to array out1 to coexist with another reference to the same array. We categorize program tokens into 3 types for grading. Root cause tokens represent where a safety rule is violated. Relevant tokens are those close to or related to the root cause, but do not directly cause the program error. Considering participants might accidentally highlight accurate tokens close to the root cause, we do not penalize the selection of relevant tokens. Irrelevant tokens have nothing to do with the root cause. We compute a score for each highlighting result by dividing the number of highlighted root cause tokens by the number of highlighted root cause tokens and irrelevant tokens. The average highlighting scores fall in the range from 0.39 to 0.75, indicating that identifying error tokens and applying RAS safety rules are challenging in general. Thus, the results confirm finding 2 of the empirical study. To confirm that RAS compiler may not provide all necessary information to debug safety rule violations, we show some participants with enhanced error messages to check their performance. Originally, this base program does not explain how to borrow array elements. We enhanced the error message by adding information to explain out1 is an array and it can only be borrowed as a whole. We show the original error messages and the enhanced error messages to 2 groups of participants. When inspecting their performance when using text to explain the root cause violation, we find that participants with enhanced error messages perform significantly better than participants with the original messages. Moreover, 4 participants explicitly mention the actual information we provide in their answers. Here's one of their answers. These results confirm that compiler error messages may not contain all necessary information for RAS programmers to debug safety rule violations, and that providing more facilitating information can improve programmers' performance. Let me conclude my talk. We conduct the first empirical study on RAS-related Stack Overflow questions. We build a taxonomy for root causes of safety rule violations, identify cases where a safety rule is more difficult to apply, and evaluate the helpfulness of the RAS compiler when debugging safety rule violations. We conduct an online survey on Rust programmers. To validate the findings in the empirical study, we design program variants and enhance compiler error messages by providing more facilitating information. We successfully confirm many findings with statistical confidence. In the future, we plan to resolve the identified challenges by automatically fixing safety rule violations and visualize information related to Rust safety mechanism. Thank you for watching. We thank NSF and Penn State to support our research work. You can find more in our paper and our artifact.